I'm very happy to tell you about some of the efforts that's been going on in my group together with many friends, collaborators, trying to make use of machine learning tools to learn from quantum matter data. So when we look at crystal material, we don't think of it as having large information content. We often specify the types of atoms involved, space group, and that's it. That's just few bits of data. However, that's because we are assuming perfect crystal. If you think about the possibility of defects, possibility of distortions, possibility of domains, once you start to take these things into account, vacancies, the information content actually become extensive. And extensive means it grows with the number of degrees of freedom. Now, on top of all of the atomic position issues, if you add electron distribution, then it's really extensive. And to make it concrete, if you look at the print content of Library of Congress, the amount of information in some crystalline material is already like more than square of the total information content in the Library of Congress. So it makes sense that you know, in order to be able to make understand these materials and try to make predictions, it makes sense that we want to be able to extract as much information as possible. And through those efforts of trying to extract as much information as possible from this large information content, various tools have been developed, and we've worked hard to access larger and larger volume of data. Now, with the development of new types of tools, new types of measurements, and better detectors and better beam lines, what's coming are data-driven challenges. For instance, we have now quantum systems available. This is IBM Q, and it's wonderful. There are qubits, but then you know that only thing we can do with those to figure out what's going on is projective measurements. And in order to figure out what kind of state the system is actually in, you need to make lots of projective measurements, and the space that you're trying to reconstruct is very big. Tunneling density of states in 1962 was measured through macroscopic tunnel junction as such, and the only data we would get out of each measurement was just a curve. And we understand every aspect of this curve, not just the why there is a gap, why there is a peak, but all these wiggles. Understanding, being able to model this data in detail gave us great confidence that we understand what's going on. But because it was a curve, it was possible to model. Now, fast forward, and now we have atomic scale resolution using vacuum as a barrier, tunnel barrier instead of macroscopic tunnel barrier. And you have, if you think of it in each energy, these many layers or many BIDV curves. Now it is impossible to try to model this, and now how do we deal with this? X-ray diffraction in 1913. This is from the Proceedings of Royal Society, paper by Bragg, Mr. Bragg, and Dr. Bragg, father and son. And this is a plot from that paper. X-ray diffraction in 1913 was looking at these kind of curve as they changed the angle, tilt angle of the sample. And they were awarded Nobel Prize for coming up with probably the first most successful forward modeling ever, which is called the Bragg condition. And we now learn Bragg condition in introductory physics, but this was kind of, okay. So now this famous formula that we learn in undergraduate physics is simple and successful, but it was successful because the amount of information that we were trying to capture was just these peaks, the location of peaks. It's a small amount of information. But like I said, we want to understand defects, we want to understand surface states, we want to understand different layers. So now we collect much more data than what Bragg and Bragg were doing. And so this is, let's see if I can get the movie to work. How do I get this? Oh, this is movie. I'm not sure if I can get it to work. No. Well, this was supposed to be a movie which was going to spin this crystal produced by my collaborator, Ray Osborne. But the point is, as you rotate crystals these days and use a high energy incident beam, look at the number of reciprocal Brillouin zones that it's covering. This one arc is the Brillouin zones that's getting covered by one angle position. And as you rotate this crystal in 0.1 degree increments, you're collecting terabytes of data. And this is what the data looks like. Just looking at about 20 units, 20 Brillouin zone by 20 Brillouin zone by 20 Brillouin zone. So that's 8,000 Brillouin zones. And there are distribution of intensities. And because it's hard to visualize 3D, if we project and look at how the intensity is distributed, you're seeing this kind of data. So what my group have been focusing on for the last couple of years is to establish ways of going from these experimental data that are either spatial pattern-like because of the imaging experiment, or high volume because of diffraction type of measurement, or something that's just hard to model, to theoretical understanding. Simple things like trying to figure out what is the right way to think about charge density wave, or just even making use of the very basic principle, such as that we are supposed to minimize Helmholtz free energy. And trying to see, by making use of data science tools, can we learn more from larger volume of data or complex data that we're now capable of measuring. So if you want to take note of one slide to get a full scope of all the things that's been going on in my group, this is it. And I have highlighted, these are March meeting abstracts. My group members have not been able to give their talks, but they've all uploaded the slides on the APS site. So if you're interested, you can go find out a little more about each of those work. I'm going to be mostly talking about this work on STM data analysis, doing hypothesis testing, and X-ray XRD analysis, trying to extract order parameters in an unsupervised way. But we've also been working on scanning transmission electron microscopy data, STEM data analysis, which is also a kind of inverse problem, together with David Muller. My student Peter Chow, who's here, has been working on tomography, quantum state tomography with attention network, a type of neural network architecture used for machine translation using IBM-Q data. And we've been also looking at simulated data from quantum Monte Carlo simulations, trying to see if we can use neural network to learn about the quantum critical region and non-Fermi liquid transport. So now, before I go further, when people ask me, so how do I go about if I have a problem and I want to try to use machine learning tools? What I like to say is that machine learning tools, like any other tools, all tools are purpose-driven. So these are examples of wonderful tools. Drill is a wonderful tool, and the chainsaw is obviously a wonderful tool. But if you have a wonderful chainsaw, but you want to make a hole in the wall, you don't want to use the chainsaw. So depending on your task that you're trying to accomplish, you have to think about what is my problem and how would I accomplish that, meet the task the best. And sometimes it may not be the most high-fashioned tool that you need. Sometimes it could be something that's simpler, that does the job better. So it's a very pragmatic approach. So supervised machine learning for hypothesis testing. This was work largely driven by my former postdoc, Yi Zhang, who's now in Peking University, assistant professor leading his new group. And you can find more details about this work from this paper. The starting point was that often when our experimental colleagues do experiment, they've done all their hard work and have their data. First thing they think about is that, so how should I think about this data? What is the right way to look at this data? Which theory describes my data best? Maybe you were really lucky and your data looked exactly like your best friend theorist's prediction they drew on the whiteboard. But I think my understanding is that people are rarely that lucky, and you get something that's much more complicated than anybody dreamed of. And you want to see, okay, this does not look like, neither my friend A's scribble nor my friend B's scribble or hard calculation. So how do I go about deciding which one of those theories are best capturing my data? So this is STN data on pseudo-gap state of high-TC cuprates. And the two competing perspectives would be, should I think about these modulations as coming from weak coupling of Fermi surface instabilities, or should I think of it as strong coupling real space picture starting from local moments and doping holes? And the conventional approach to looking at this kind of modulation data is to do a Fourier transform and try to compress the Fourier transform down to some peak location of a line cut. Now, if you try to do that on this data set, what you find is, what you find is this kind of broad distribution, just looking at the real amplitude, because you do Fourier transform with your computer of a real space data, you have the full phase information. This is looking at the amplitude, and you make a line cut along this line, going from here to there. That line cut is giving you this kind of jagged, complicated plot. So it does not help you identify, okay, should I think of this jagged thing as having an underlying leader peak position here or there, and or is it moving? But at the same time, when you look at the data, our eyes, all of our eyes, see some motif here, like when you look at wallpaper or modern art. And the motifs are obvious to our eyes, but we see the same thing, but we don't know how to pull that out. The process of pulling it out in human mind gets loaded with a lot of other processes, bias, social interaction, I don't know. So why do we care? Well, because this data set is supposed to be giving us a picture of what's going on in the enigmatic pseudo-gap phase. So what can we do? Well, it turns out we can think about what a charge density wave pattern should look like. We just think of it abstractly as a pattern, because all our theoretical understanding of charge density wave tells us that, okay, the charge density wave is going to have some modulation with some wave vector q, and there is going to be phase disorder, either due to smooth fluctuation or due to topological defects. And there will be amplitude disorder that's due to smooth disorder or smooth noise or topological defect. So we can model this, and we can think about what a pattern that's guided by some organizing principle will look like. And these are four different categories that seem reasonable given the spread of the Fourier transform, each associated with different leader wavelength. So this is what we call category 1 with this wavelength, category 2, category 3, category 4. And category 2 is the only one that's period 4, so that's commensurate. Commensurate wave vector is what we are associating with real space. Incommensurate wave vector is what we are associating with momentum space. So can we think of a machine that can be trained to recognize each of these candidates? And can we try to see whether that machine can try to pull out having been trained objectively to look for a motif, can we ask this machine to tell us, so which one of these motifs are you seeing? And this process of working with neural network and training is kind of guided by how we thought about brain. The neural networks do not reflect brain. Brain is extremely complicated. But what neural networks do is these are functions that we set the parameters, not manually one at a time, but by giving feedback. And I often like to give a sort of illustration of how this works, how the decision should be made by the neural network, artificial neural network, comparing it to how a decision should be made by a kid. So decision is determined, it's determined by weights and biases, and there's nothing uncertain about it. It is definite. Once you have given weights and biases, it's a function, it's going to have a definite outcome. However, we don't know yet what those weights and biases are, and it's going to take the input. So what are the inputs this kid is going to take? The kid is going to think about how long has the food been on the floor? Is mom watching? If mom happens to be the bad cop, like in my family, how sweet is this food? How green is it? You know, these are data the kid is taking, and the decision the kid has to make is simpler than trying to decide whether STM pattern is real space driven or K-space driven, but the decision of whether to pick it up and eat it or not. It's simpler bimodal. So what's going on in the kid's head? Well, I cannot see it, but if I think it is a neural network, what's happening is there are different neurons, say one neuron in, say, amygdala. It's going to take these inputs and it's going to weigh each of the input component, which I made into a vector, by different weight depending on the neuron. So weight is a matrix, and there will be a bias that's specific to a particular part of the neuron. And when this is combined, which is a linear function, the neuron is going to fire or not fire, which is a nonlinear function. So this whole matrix multiplied to the input vector with the bias vector added goes in as an argument of a nonlinear firing function. And then different weight matrices and bias vectors exist for different neurons. It gets all collected. At the end of the day, artificial neural network is nothing but a function. This is a function, and it's got weights and biases, a lot of parameters. So how do we set the parameters? We set the parameters of artificial neural network just like how we set the parameters of my children's brain's neural network. I cannot go in and set the weights and biases, but what I can do, the only thing I can do is to give them feedback, and the only thing I do to neural network is also give them feedback. We start with label training sets. So these are the conditions under which it's okay to eat. These are the conditions under which it's not okay to eat. And they will go through a lifetime experience of going through their own decision making, which leads to the particular output of the function, and comparing that to the desired output. And what I do when I see the kid do not what is desired, I tell them, well, there's a distance between what you've done and what I desired. And we try to minimize that distance. And that minimizing the distance is done through adjusting the weights and biases through stochastic gradient descent. And this is iterated. So now you apply the principle to the STM data. We're going to look at doping dependencies. We first trained the neural network with the simulated data that, as I've shown you, with 4 possible options. And now we give the actual data as this one at different dopings, whose Fourier transform look like this, and let neural network come to the decision. And on the rightmost side is the neural network's decision. And it is showing that category 2 had the highest rate of being called out. We've trained 80 different neural networks, meaning starting from different initial conditions, and we polled them. So which one of these do you think is the most likely? And they would each answer, and we look at the total outcome statistically. So now we move up in doping. Still, category 2 is most dominant. Move up in doping, still category 2. Period 4 is most dominant. But by the time we reach near optimal doping, they all become neck to neck, meaning none of them are particularly dominant. And there is an interesting thing that one might have noticed looking here, that there is a clear discrepancy between red and yellow. What are red and yellow? Those are two different orientation that we've given the data. So now collecting all of it and giving the entire energy dependent data set, what we end up with is that, oh, the category 2 becomes clearly dominant as the energy scale reaches the pseudogap energy scale, and one direction is different from the other. And that is giving us a result of this hypothesis test. The outcome of the test is that we started with this data set and we wanted to test these two hypotheses, case space driven nesting picture versus real space driven commensurate density wave. And our exercise with neural network supports that unidirectional lattice commensurate period for charge modulations better describe the data. So now I'm going to switch gears and move on to unsupervised machine learning for high volume XRD data. And this work was done in collaboration with many people here. Kilian Weinberger is computer science colleague at Cornell. Jeff Pleiss is student. Two people who did, well, most of the large part of the work was really done, lion's share was done by my student Jordan Vendelli. And a lot of data came from Jacob Ruff at Chess, and also most of it also came from Argonne National Lab, from our collaborators, Matt Krogstad and Ray Aspen. So what are we looking at? We have this large volumes of 0.1 terabytes of data for different temperatures. And it is difficult to look at one data set at one temperature, but we want to be able to process this terabyte of data over different temperatures and discover something. Not trying to do the forward modeling like Bragg and Bragg did, because that's impossible for this complexity of this volume of data. So what are we going to do? The task is that we've got all this 8,000 Brillouin zones, and we want to search for special cues at which something interesting is happening. This is a difficult problem just because of the sheer volume of it, okay? I used to call this a needle in the haystack problem, but I quickly realized very few of us have any experience with haystacks, so it doesn't come to us live. Here's an experience that is very close to my heart, searching for that special Lego piece in a pile of Lego stack. So how should you do this? If you've ever done this, you will know trying to pull out one piece at a time and checking whether that's the right piece is a very bad idea. And that's a manual approach. But the right thing to do when you face this problem, most of us almost intuitively resort to the following approach, which is to sort. You want to sort by some criteria. In this case, we've sorted by color. And if you knew the color of the piece that you were looking for, you can focus on just one color. Okay, so we want to take this approach to the high volume X-ray data. But what is going to play the role of color? For Lego pieces, it would have been either color, or whether it's a person, or it's a shape. There are some obvious choices. What could be our choice for X-ray data? What we turn to is the simple foundational fundamental principle that, okay, emergent phenomena that we're after, some ordering, is ultimately competition between energy or Hamiltonian and entropy that's driven by the pressure of temperature. So the Q points that have to do with some emergent phenomena, some ordering, is going to give different temperature dependence in its intensities compared to rest. I don't necessarily need to know what it is. I don't need to try to model it. I just need to know that I should be able to keep track of intensity at each Q as a function of temperature. So at each Q, if I'm going to track their intensity as over some 20 temperature values, I have a series of length 20 for each Q, and I'm going to keep track of them and see whether I can sort them. And this approach was, this idea came from my colleague Kilian, and the idea was that let's make use of what's called what's so-called time series clustering. So these are audio data recording of 2 different people, 3 data sets, and 2 of them belong to one person, 1 belongs to another person. And the way you figure out which one belongs to which, when we hear, we know. But if we want to do it through machine, the way it works is through time series clustering, that is treating this whole data set over the span of time as a time series. And you cluster, try to see whether there are different types of clusters. And the result comes out to be this. This one is from a male. These ones are from female, but the gender does not matter. We cannot try to figure out what is it that learned, but there is some qualitative difference. So we're going to try to take this approach and see if we can accelerate discoveries from this high volume, comprehensive X-ray data set. Now, manual approach, looking at one Lego piece at a time, takes weeks, months of inspection by eye. And I've even had that experience with Lego too. It was depressing. I can imagine how unmotivating, uninspiring would it be to just look at different slices. We don't want to do that anymore. We want to accelerate discovery by discovering models and clustering simultaneously without any external bias or imposed. Now, what does data look like? So now this is treating the data as temperature series, not time series. So for different cues, for all the cues that we looked at, we plotted the intensity as a function of temperature, and it's a mess. If you look at it in reciprocal space, a cut, because it's hard to visualize 3D, it looks like this. There is some spread, and there are higher sharp peaks near the brag points, but there is also noise and there's diffuse peaks. Now, the first thing we need to do is, because if you're to keep track of all the points in Q space, it's a grid of large data point. It's like looking at large population where most of them are not doing much. So we have to reduce the volume that we're trying to keep track of. And we also have to rescale, because the scale range is enormous, between, what is this, 100,000, 10,000, 10,000, like, and 10,000 is still not keeping the peak. It's way too big. So what we do is we first, we used, came up with a thresholding scheme, which looks at data whose intensities are not dominated by low-lying, always low-lying noise. And after thresholding and rescaling, we arrive at this kind of data set that still does not look immediately obvious what kind of different behaviors there are. But we've reduced, because we've thresholded, we reduced the space volume of Q points that we have to keep track of to just the pixels that are covered by yellow. And then we use the Gaussian mixture model, which is a simple and robust clustering approach that can handle different functional behaviors. For if we have n temperature measurement, T sub n temperature measurements, we treat the whole series as belonging to n-dimensional vector space, a point in our n-dimensional vector space. And we model the distribution of these n-dimensional vectors over the population of Q points that have survived the thresholding using multivariate Gaussian. So the multivariate Gaussian is defined by its mean and its variance, the covariance matrix, and this mean is a vector that also belongs to this n-dimensional space. Covariance matrix is n by n matrix. And this is a model that we're going to use. And we're going to try to discover if there are different means and covariance matrix that describe different qualitative behavior. And we discover those models by using this log likelihood, maximizing the log likelihood, where this IQ of t is the trajectory at that Q, and we are thinking of different clusters, so we allow for mixing weights over different clusters, and each cluster is characterized by its mean and covariance. And we start with some initial value, but we try to maximize this log likelihood. That is, we try to find a model that best captures the actual data. And the only parameter that we set at the beginning is the number of clusters. And through maximizing the log likelihood with the expectation maximization, we arrive at the result. So now what have we learned? How many more minutes do I have? I ran out of time. Okay. All right. So this is the material that we looked at, which is a pyrochlore material, which has recently become of great interest due to this multipolar nematic possibility. And the bottom line is, this is what we can do in 10 minutes of handling, processing this terabyte of data. And what you can see is that this cluster that's been discovered obviously looks like an order parameter. And that is indeed associated with the charge density wave ordering at this temperature. But there is a lower temperature ordering that's been mysterious, because it's been suspected it's an ordering that does not change the unit cell size, which means it's not going to give rise to a new peak. What we were able to learn, though, through this clustering is that what this distortion at this lower temperature TC1 amounts to is a change in the shape of the peak. There is a shift in the change in the shape of the peak. So if you go from high temperature to low temperature, at this high temperature, about 200 Kelvin, there is unit cell increase, which leads to new peaks, which we discover. And then you go to the lower temperature transition, at which the shape of the peak changes. So this means we are now capable of detecting subtle intra-unit cell changes, which we wouldn't have been able to make statistically meaningful if we had only one Brillouin zone to look at, because it's a very small peak, very tight peak that we're looking at. But having thousands of Brillouin zones, we could convince ourselves that this is something that is indeed going on in the system. And on that note, let me just conclude. I've talked about using various machine learning tools to learn quantum emergence from large volume or complex data. I talked about using supervised machine learning to do a hypothesis testing and discuss the theoretical candidate for order parameter, the nature of the order parameter that gave us new insight into the complex data. And I have also talked about unsupervised machine learning. There is a clustering approach that can handle large volume of data to accelerate discovery. And on that note, let me conclude and thank you for your attention.
Yeah. So before we go into the questions, Antoine wants to address.
How you want to do it before going to the questions? Well, that's what I'm going to say.
Well, no, well, okay, let's finish the session. So how many questions are there questions here for everybody?
You got to come here, talk to the microphone.
Okay, in the neural network calculation, did you vary the hyperparameters? I mean, how many hidden layers do you have, and so on? And
right.
What is the final network?
Yeah, so the final network we used was what I specified in the slide, which is ridiculously simple. Single hidden layer with 100 neurons.
But did you vary?
Yeah, we tried varying things. We tried working with much more complex neural networks, such as convolutional neural network. We found that this simple neural network does the job. That's what I meant by hammer.
So in experiments, there are sometimes systematic errors that that even the experimentalist is unaware of.
Right.
Maybe some temperature drift, some
yes.
pixels that
yes.
are off. So are your techniques useful for identifying them,
yes.
or do they get biased by them?
So that's a wonderful question. So with this X-ray data clustering, it was really done blindly. Those of us who analyze the data didn't know what kind of artifacts are possible. So we just cluster everything and we report back to our experimentalist colleagues. And then sometimes they say, that's weird. And then we realize, oh, there was a rod, there was, temperature shift. So what we are able to do is to look at the data and comprehensively, like all of it. We look at all of it and discover what is a meaningful, statistically meaningful trend. And then the physicists have to come back into that loop. The experimentalists have to come back and say, okay, which of these are meaningful? And then, and there were several of such experiences. My student Jordan got really excited. Okay, I found something. And then we talked to our colleague, and he says, that does not make sense. Oh, there was some, misalignment of blah. So there has to be that kind of cycle. But the hope is, instead of finding there were issues 6 months after your beam time was over, you want to do it right there. While you're there in the beam time, while you're having coffee, you finish this, and you look at what are making sense and what are not making sense. Am I doing measurement in the best ideal setting, or should I push a little further in temperature? And be able to make those decisions right there. That's the goal. And what we are working on right now is trying to make this this algorithm whole package, which has pre-processing and so on. We're trying to make it kind of self-contained and user-friendly. And eventually we're hoping we can make it available to people at BeamMinds.
So let's thank Una for a nice talk.